So, hi everyone. Here's a SIG Scheduling maintainer session. My name is Kensei.
And my name is Dominik.
So today we're gonna going through how the scheduler works, the recent biggest initiative about the workload-aware scheduling, and then the recent other features as well. And then lastly, we're gonna talk about a few sub-project updates as well. So today we have a lot of things to present. So maybe we cannot leave the time for the question later, but we're gonna, earn the room after the session so that everyone can ask any questions for us. I have to start my timer. Yes, so let's start it. So we are a SIG scheduling group. Basically, we are responsible for components that make pods placement, which is in Kubernetes itself, that is Kubernetes scheduler. And also as a sub-project, we have Kueue, which is kind of, workload-aware scheduling stuff. And then we have desk scheduler, we have simulator, we have Quark, we have WASM extension, and we have others as well. So here we have a scheduler, which is a main component for us. Basically, this is the component that decides the pod placement. So basically, I believe that most of people like using Kubernetes are using scheduler as well. So basically, we have plugins, and plugins would be implementing those those scheduling features. So for, for example, pod affinity, we have interpod affinity plugin. And, for other features as well, we have a dedicated plugin for them. And then we have a concept called extension point. This is the, as the name tells, it's the point that each plugin runs on. And then these are major popular extension points, filter and score. So basically, each filter plugin filters out node that should not run the pods, and then score plugin scores nodes based on the some preference. So let's see how it goes. So let's say we are scheduling some pod, and then we have 4 nodes, and then we have those plugins. So first, what we're gonna do is basically filtering out some nodes based on filter plugins. In this case, node 3 and node 4 are rejected based on, based on something. And then after that, those remaining number 1 and number 2 are going to scoring phase, and then scored based on something again. And then we have a total score, and then we decide that, in this case, node 2 is the best node for the pod. So actually, there are much more extension points for the plugins. Actually, not all extension points are used in, entry plugins. So some of them are, just existing for other use cases, custom plugins. So basically, what you can do is you can have your dedicated plugin for your original, use case. If you find something, then your plugin would be running on some of those extension points, so that your pods would be being scheduled by your original use case. So basically, this green box is called scheduling cycle. This is literally the phase that decides the placement of pods. And then we have yellow area, which is called binding cycle. This is the phase that actually makes an API call to bind pod onto onto a node. And this purple area, this is just the scheduling queue. We have all the pending pods in this scheduling queue. And what we are doing is basically popping one pod from the scheduling queue, and then scheduling cycle, scheduling pods one by one. And then this URL binding cycle, it's running asynchronously, so that we can decouple the API call, which is blocking call. This is kind of for optimization performance. So yes, so this is how, like, pretty much summary of how the scheduler works in general. So yeah.
Thank you, Kensei. And I wanted to talk briefly about workload-aware scheduling. This is the effort that we are kicking off in SIG Scheduling. And why we are doing this? So everyone knows that Kubernetes is great to perform and to run various workloads. But in case of AI workloads, they are a little bit more demanding. So for instance, AI training jobs are long-living, and they require to have all pods running at the same time. So in case one pod breaks, the whole workload may break. AI inference have a little bit different requirements, but they are still very different from serving workloads that Kubernetes used to support so far. That's why our goal is to improve the support for workloads. So we want to enable running various workloads at the same time, even in the same cluster. So we want overall to improve the price performance. So make workloads running faster, more efficiently, but also to better utilize the cluster resources. So what's a workload? Workload is a basically collection of pods and resources that work together to achieve some task. So in case of AI workloads, we may have workload level requirements that apply to all pods in a workload. And those requirements are, for instance, topology requirements or nothing scheduling. So what's the problem we are trying to solve? One could say that there are many schedulers which are capable of scheduling workloads, but scheduling a workload is not enough. We need to make sure that the workload is executed reliably in the cluster, and we need to assure that. To assure that, we need to let other components understand workloads. They need to know that if they impact a single pod in some way, they might impact the whole workload. So workload-aware scheduling scope is very broad. First of all, we want to introduce generic workload object so that all the components can basically speak the same language. Once we have that, we want to support workload scheduling. So we need to support the topology requirements or gang or nothing scheduling requirements. We also need to, at some point, support workload level preemption, which is a different problem that we know from pod preemption that works based on a single pod priority number. In case of workloads, it will be much more complicated and more dynamic. Even preempting a workload doesn't necessarily mean that the whole workload needs to disappear. We are prepared for rescheduling a workload, which may mean that only some part of a workload is rescheduled. So it depends what are exactly the workload requirements. We want to also integrate auto-scaling into scheduling. because scheduling a workload will become a more complicated thing. So we also want to be able not only to schedule on existing infrastructure, but also on potentially available infrastructure, which can be provisioned later. We want to support resource reservations and scheduling simulation so that we can allow higher level schedulers, which we call orchestrators, to actually do cluster optimization and be able to schedule not just a single workload, but a collection of workloads together so that we can achieve a little bit better placement than if we consider each workload separately one by one. So what we did in 135, we introduced workload API. This is the initial version which allows us to model gangs and specify what is the minimum number of pods to make the gang schedulable. We also implemented simple version of gang scheduling, which at the moment allows us to block binding until all pods are scheduled. So this means that we can separate logical scheduling phase from the binding, we can call it now actuation of the workload. It's important in case of workloads because we want to avoid a situation when we started binding pods that belong to a workload without making sure that all of those pods can be successfully scheduled. So what can we expect in the next release? We definitely want to expand the workload API. We may need to support gang of gangs to be able to model more complex workloads like job sets or leader worker sets. We also want to support topology constraints. For that reason, we will introduce a new phase to kube-scheduler that should be capable of scheduling the whole workload in a single cycle, so in a consistent cluster snapshot. We also want to break down the preemption into two parts. One part is more logical. The second part is the actual the actuation. So the actual preemptions should happen later after we make sure that the workload as a whole can be successfully scheduled. And of course, we are working on workload-aware preemption, on integration with auto scheduling, simulation API, and reservation API. Now I can show briefly what's the difference between pod-by-pod scheduling and gang scheduling. So in case of pod-by-pod scheduling, each pod goes individually through the scheduling and binding. That means that binding always directly follows scheduling. So we schedule one pod, another, and the third one. In case of gang scheduling, we don't want those pods to leave the scheduling phase until all required pods are successfully scheduled. And only when all got scheduled, then we can allow them to start the actuation. And the actuation, as I mentioned, may require starting the actual preemption of the victim pods. It may mean triggering autoscaling. It may mean waiting for resources to be provisioned. So in this way, we can assure that the workload is consistently scheduled. So this is just the beginning. It will expand, and stay tuned. Kensei.
All right. Thanks, Dominik. So from here, we are going through the other recent major updates from the last 2 releases. We have those features, and I'm gonna skip young scheduling. We talked a lot, and then also many DLA features are also on our SIG scheduling, but we won't touch it. I believe there should be other session, like maintainer session for device management working group. So
Yeah.
I haven't checked, but I think so. So yeah, please join that one if you are interested in DLA especially. So we are focusing on the remaining 4 features here. So the first one is the opportunistic batching. So this is a new feature introduced as a beta in 1.35, hopefully. I'm saying hopefully because we are still working on it, but hopefully it should be in. And then the motivation here is pretty simple. It's that we often have multiple parts from the template. For example, job, I don't know, replica set or many other resources that managing parts. They have template, and we are creating parts from template. So, do we really have to evaluate all nodes every scheduling, or what if we can optimize some fast implement some fast path for those parts? So remember, this is my previous page that I explained initially. So when the scheduler decides the best node, it actually has a list of total scores of the nodes that already passed the filtering phase. Okay, so what we have to do here is that basically, okay, so part 1 is scheduled, and the scheduler gets the list of node scores, and then part 1 goes to, let's say, node 1, which is at the top of the list. And if the next part, let's say part 2, is the same as part 1, we can just schedule part 2 onto the second node. Second highest scored node. Or if not, we are gonna just remove the cached node scores. So we know that this is pretty simple example, and we have to have some assumptions to apply this fast path to those pods. Let's get into detail. And first, what is same here? What's the definition of same here? Because every pod has for example, different name, of course, different ID, of course, and might have some different, I don't know, environment variables, and might have some different annotations, for example. How should we determine if 2 pods are the same or not? So basically, when we are saying same here, it means it's the same from the scheduler's perspective. So for example, UID is more usually not scheduling related, and environment variables as well, they are not basically related. And on the other hand, for example, I don't know, topology area scheduling constraints, they are obviously scheduling related in a pod spec. So it's kind of like implementation detail, but what we are doing is basically we get a new concept called signature, and we implemented a new function. Maybe you can call it a new extension point, which is called a sign pod. So sign pod basically gets a pod and return a signature. And if the signature returns, if, for example, signatures are the same for multiple pods, that means those pods are the same for that plugin. So what we can do is, I don't know, like, for example, like a sign pod of node affinity plugin, we would, like, signature would be including, of course, node affinity spec, like node affinity in a pod spec, and yeah, maybe others as well based on some different conditions. So yes, that is a concept, a new concept, sign pod. If you're developing custom plugins, you might have to implement it for your plugin as well. But basically, we are doing things backward compatibly. So if you are not implementing that new interface for your plugins, it's just, this feature is not like basically enabled. The whole feature will be just disabled. And then back to this example, if all plugins are returning the same signatures for pod 1 and pod 2, then the scheduler can say, okay, pod 2 is basically the same as pod 1 from the scheduler's perspective. And also limitations. We know that this optimization has several limitations. So the first one is, first limitation is we are right now limiting that pod 2 can go on the fast path only if it could not be scheduled onto node 1. I mean, node 1 is the place where pod 1 is scheduled. Right. So the reason is that otherwise we'd have to recalculate the score of node 1, right? So because after putting pod 1 onto node 1, node 1's score might be just changing, right? So basically we have to recalculate the score if we want to support it, and that's actually on the timeline. Like we are probably going to do that pretty soon, hopefully, but right now we are not doing it, and we are limiting this feature to be enabled only when node 1 is not schedulable, like not possible to get node pod 2.
Yeah, so in other words, we assume that only one pod can land on one node, because otherwise we cannot reuse the results of the previous scheduling cycle, because the scoring may change.
Yep, thank you. And while we are, yes, so the second limitation, pod 2 does not have any interpod scheduling constraints, which is pod affinity and topology spread. Because those features, the scores and also like feature result, they could be changed after like scheduling pod 1 onto somewhere. So basically, if we want to support this case, support those features, we have to recalculate all filtering and scoring results, which means
which we wanted to avoid.
Yes. And lastly, some like the latest cluster state changes might be ignored. They are ignored. For example, if a new node is added, then this new node is not included in the cached scoring results, right? So basically, we cannot take those latest changes from the cluster. So if for this part, we have a basically short TTL, I think it was 500 milliseconds, right?
Half a second.
Yeah. So that two old scheduling results won't be remaining. And also, we hope that this feature is also beneficial for our future workload-aware scheduling that Dominik mentioned. So basically, to pre-calculate the pod placements of a workload, we will have to check the schedulability of each pod, right? And then it's often that we can assume there were several basically same pods in a single workload. So yep, so this feature could be could make that part a lot faster. Right, so next feature, this feature is asynchronous API calls during scheduling. This is implemented in our last release as a beta feature, but disabled by default, right?
Yeah, we had to disable it in the previous release.
Yeah. And then we enabled it, we enabled by default in the latest release, 1.35. So basically, the title describes all the things. API call is, well-known bottleneck for scheduler. So we already have some features to avoid this API call to block scheduling process. One is obviously the binding cycle that I mentioned. And then the second one is the asynchronous preemption feature, which is already implemented as a beta. And now here we have this feature to make basically all API calls asynchronously in general. I won't explain it deeper as we don't have much time here, but basically we have something like a queue, which is, and also background workers, right? And then they are making actual API calls instead of blocking, scheduling cycle, and making API calls.
Right. One of the motivations is to not have any API calls blocking the scheduling cycle itself, because we want to have the scheduling cycle very fast. We can do API calls either in the background or during the asynchronous binding and actuation phase, but not necessarily in the scheduling cycle loop.
Right. Right, so this is what it is. And the next one, use nominated node name to express the expected pop placement. I mean, this nominated node name, this is already existing. So basically, this feature comes from the problem stated here. So in some scenarios, for example, you have a delayed volume binding, it could take some, maybe several minutes for pods to be bound, actually bound, after the scheduler decides the placement. So if I have, oh yeah, so it's young scheduling, but all those delayed volume binding and stuff, they are done at this pre-bind state, pre-bind extension point. So, an actual binding API call is done at the bind point. So actual binding API call could be delayed because of those delayed volume binding and also other pre-bind plugins as well. So going back. So what we are doing is we are using this nominated node name API to expose where the pod is going to before actually doing some those delayed binding and stuff. Oh, we actually, okay. So after the scheduling cycle decides the placement, the pod goes to the binding cycle, as I said. And then at the beginning of binding cycle, if a delayed binding or something will be happening there, before doing those, we put nominated node name so that external components, for example, classed out scaler, can be aware of those, like those pods are coming. So after this enhancement, for example, the classed out scaler can check if there's any pods that are not bound yet but are coming. That prevents the problem that are stated in this slide. Like basically, cluster out scaler right now cannot know these pods are coming, so it could delete some nodes. But actually, those nodes are already reserved within scheduler's internal cache. So yes, this feature would be improving that part. And the last enhancement is extended toleration operators for threshold baseband placement. So this is a new feature introduced as alpha in this release. And then it basically supports a new operators in tolerations to support the numeric comparison. It's very easy to understand by the example here. So let's say you have a SLA in a node 10 and value says it's 800. And then if you want to schedule, if you basically want to allow pods to go to, for example, nodes with SLA more than, higher than 750 here, then you can say greater than 750, then this pod can be going to that node. Right, other major updates in the previous releases. So the first one is my favorite one, actually. So right now, basically when you develop custom plugins, you have to import Kubernetes repository because, there are scheduling framework interfaces, there are some types. Those were implemented in the Kubernetes repository. So basically, custom plugins had to import those libraries. But so from last release, 1.34, we migrated those types and interfaces to the staging repository so that everyone can implement their custom plugins with those staging repository, not Kubernetes itself. It will be making you easier to maintain your plugins. And the second one is just that queuing hint is now GA at 1.34. Right. So from here, we're gonna quickly go through all the actually a few of sub-projects of us. The first one is Kueue. So it's an AI workload level scheduler. So it supports gang scheduling. It also supports some, topology-aware scheduling that we want to implement in Kubernetes scheduler as well. And then also it supports some multi-cluster workload dispatching, which is called MarchQ. Also, it works as a resource cooler manager, checking the resource usages and then admit or maybe suspend the workloads based on that. And also it supports some resource preferences as well and fair sharing as well. And those more rich features implemented in Kueue. So what's new in Kueue? So recently, topology-aware scheduling is promoted to beta, and also it now supports two-level scheduling. And regarding MarchQ, it newly supports a dispatcher API to extend how to dispatch workloads in a kind of custom way. And there's another one generic job adapter. This allows you to implement adapter to adapt your custom jobs working with March queue. And then it supports resizing and also DOA. And the next critical changes in the next minor release would be we are going to promote Q API version from V1 Beta 1 to V1 Beta 2. And it's going to be around November or December. And for the future, we are planning to graduate APIs to GA and probably in the next year. All right, so if you have any questions or discussions on Q, we should have maintainers in this session room as well. And then also there's a Q pavilion in a, like around the solution area where you can, meet and discuss with Q maintainers. And the next one is desk scheduler. So scheduler evaluates scheduling constraints only at scheduling, but desk scheduler is watching the already scheduled pods so that we can maybe like reschedule some of them based on some policies. So what's new here is we now have a new pod production configuration to move the basically move the previous approach to a more like intuitive and unified way to define the production rules. All right, that's all. We are exceeding the time actually. So to join us, we have a Slack channel in a Kubernetes organization, SIG Scheduling. You can join it. And also we have community meetings every week. One is for Asia, Europe friendly, and the other one is for the other areas. Right, thanks. We are exceeding time, but we'll be around this room, so feel free to ask any questions for us. Thank you so much.
Thank you.